Okay, calculating pH of a weak acid. This is a video I expect you to need to re-watch. It is not immediately apparent. There's some math tricks to it. I'm going to show you why those are there, and I'm going to show you a shortcut. So the first thing I'm going to show you is how to figure out the pH the most exact way. Remember, we're not going to use that method. There's an easier, simpler method, but we need to understand the first method to know why we can make those assumptions. So remember that dissociation constant, that Ka, we're gonna use a make-believe acid. We're just gonna say Ha, and then A is just whatever. So our dissociation constant is gonna be that H plus times that A minus all over the initial concentration of that acid. Okay? So that's our constant there. Remember, our pH is equal to the negative log of the concentration of hydronium ions. So we need to figure out, for a weak acid, what is that concentration so we can figure out the pH. Well, excuse me. Well, that hydronium constant is going to be found in this math equation. So to understand this better, look at how confusing it is. I mean, we've got elements in a math equation. It's annoying. It's just so taxing. So if it helps you, replace these with just letters. So something like, okay, instead I'm going to say K equals X, Y over Z. Boom. Same thing. Could you rearrange that to solve for X? Sure you could. There's even a trick to make it easier. Because remember, if this disassociates, let's use another color to see that. If this HA, let's write the hydrolysis reaction up here, this HA turns into H plus and A minus, well, then there's going to be the same number of H plus as A minus. It's going to have the same number of hydronium as the conjugate base. Remember, this is the conjugate base. This is the base on the other side. That's why this whole thing works the way that it does. So this H plus and A minus, their concentrations are actually going to be equal. That is a great first step. If those two are equal, well then that's like saying over here that X equals Y. So then really, if I were to rewrite these equations, then I would say K equals X squared over Z. There we go. So right here, I'm going to rewrite this. I'm going to bring it down here. I'd say Ka equals the concentration of H plus squared over HA, or the concentration of HA, sorry. So there we go. Hey, that's already easier. And this is something that we would know. We would know the value of Ka because we could look it up in this table here. We would know the concentration of HA because we would have added it to the solution. So we would be able to calculate the concentration of H+. Let's go through that. The key here is to remember that this HA, we're going to lose some. Now that's important. This HA, I'm going to lose some of that because it's going to go through this hydrolysis reaction. How much of that HA am I going to lose? How low is my concentration going to get? How much lower than its initial concentration? Well, it's going to lower by the amount that it disassociates. So really, the final concentration of this isn't quite just the initial concentration of HA. This is going to be the initial concentration of HA minus the concentration of H+. Okay, now we're ready to boogie. Let's rearrange this equation. Let's rewrite it one last time on a fresh board. Then do some math. So I've got Ka equals concentration of H plus squared over concentration of HA minus concentration H plus. There we go. So first thing I'm going to do, get this whole thing, multiply both sides by it so I can get it over to this side. Just doing math. So I'm going to have Ka times concentration of HA minus concentration of H plus equals H plus squared. Okay, next step, multiply this by both of our variables in there. So we go Ka times HA minus Ka times H plus equals H plus squared. One more step. Okay. Now, how do we solve this kind of equation? Have you ever seen this kind of equation before? I mean, let's gotta break this up. Let's go H plus, let's call that X. Let's call that X. Say that's X, so X squared equals Ka, let's say that's B. So we're gonna have X, we're gonna have B minus then HA, that's something completely different, times Ka, let's just call this whole thing C. And then let's say there's a 1 right here, so we'll call that 1A. Well, that's a quadratic equation. Hey, look at that. I could just say AX squared and then plus BX minus C equals 0. And now I've got a quadratic equation. You could use the quadratic formula to solve it. You could solve that for X. So if we were to put the same thing here, if we were to say, oops, careful. If we were to use these initial variables again, well then I would have 0 equals H plus squared, then plus Ka H plus minus Ka HA. Now remember, these are all known values except for H plus. Everything here, so let's underline everything that's a known value. These would all, we just have numbers for these. So the only missing variable would be that H plus. Now remember, I said this is not the way we're going to do it. We could solve this, we could go through and solve this, and this would give us a very accurate concentration for hydronium. However, what you would find is that for almost every one of these weak acids, this number, this HA minus the H plus, it really isn't that much. It really isn't that much of a difference. It's so tiny. The change in the concentration of HA is so tiny, it might as well not be there at all. And what I mean by that is, if I started with, let's say 5 molar is my concentration of HA. And that's what I started with. And then it disassociated. These acids are so weak that it might only lose 0.001 molar. So the difference between 5 molar and 4.999 molar is so small that we might as well not even account for that. So let's go back to the beginning here, before we actually started moving this equation around, and let's pretend that this right here is so close to the initial concentration of HA that we're just going to use the initial concentration of HA. Would that simplify things? Let's try it. So instead of writing out the whole quadratic equation, I'm just going to say Ka equals concentration of H plus, that's still going to be squared. Remember, we had that trick from before. We still square that, but then we're just going to divide it by the concentration of our HA, our initial acid concentration. Okay, now let's rearrange that. So now I multiply both sides by HA, so I've got concentration of HA times Ka equals H plus squared. I just square root both sides. Oh hey, wait a minute. That's easy. Square root of HA times Ka equals concentration of hydronium ions. There's a lot of work to go through, but at the end of the day, that's pretty simple. Considering this is what we started with, that's a really nice simplification for something that's actually a really complex process. That's it. Square root of the concentration and the equilibrium constant. If we want to figure out the pH of a weak acid, first remember, pH is found by negative log of H plus equals pH. This is going to be for a strong acid. So this is strong. All right. What's the equation going to look like for a weak acid? Weak. Well, it's just going to be the negative log of the square root HA times Ka. That's going to be equal to pH. Okay, let's look at an example. I'm sure everyone's jonesing for that. Remember, I said you're going to need to watch this video multiple times. But let's go ahead. Let's see if we got a clean board here. Yeah, this one. So, coming back to this page, this is really where we're going to be actually practicing this. This first page, determine the pH of the following strong acids. You should go ahead and do that. You should be able to do that on your own. In the previous question, the actual type of the acid was not needed to calculate the pH of the acid. That's because these are all strong acids. They're going to completely disassociate. It doesn't matter which acid it is. All we need is that concentration. For a weak acid, there's two factors that affect the number of hydronium ions that get produced. What are they? Those are going to be what we have under the square root. That's going to be our negative log of the square root of our concentration of our acid times our equilibrium constant. So these two, this and this, those are the variables. Those are these variables that affect that pH. So now, determine the pH of a 0.1 molar solution of HC2H3O2. If I remember correctly, that's acetic acid. So let's go ahead. We've got 0.1 molar. Okay, so our initial concentration, HA, is going to equal 0.1 molar. All right, and then we just need the value of Ka. So for H, I'm going to write that down because I'm bound to forget it. HC2H3O2. What is the Ka for that? We're just going to look on this table. I'm going to go down this table until I find it. H. Good enough. Thank you. It's because it was different. Ethanoic acid. Okay. Ka 1.8 E negative 5. So there's our values for it. Now all we have to do is plug these in. So I can say the negative log square root, I'm going to put everything in parentheses, of 0.1 times Ka of 1.8 E negative 5 equals pH. So let's grab a calculator and put that in. So to put this in on the TI-89, you've actually got to type in the log manually. Put your negative sign first. So it's going to be LOG, and then we've got second square root right there. Square root of 0.1 times 1.8 E negative 5. And that gives us a pH of 2.87. So our pH equals 2.87. There we go.